in GET and with HCC from 2008 to 2009. He worked as an assistant professor with our institute, that is Rajaram Bapu Institute of Technology, Rajaram Nagar, Sakrale, from 2011 to 2013. He is currently working as hardware architect and firmware lead with R&D Smart Infrastructure, Siemens Limited, Mumbai. His interest includes power electronics converters, HVDC, e-mobility, photovoltaic storage, and electric drives. During his PhD research at Siemens, he has published more than 15 papers in the reputed journals and conferences. He has more than 5 patents filed. So we are really happy to have such an expert in our domain of power electronics, and I invite him to benefit you all so that you will get an industry exposure and skills what are the ongoing technologies as well as uh, recent trends in our domain of power electronics. And this is an attempt to bridge the gap between industry and academia. So, Mahendra sir, you are welcome on behalf of Department of Electrical Engineering of Rajaram Bapu Institute of Technology, Rajaram Nagar.
Thank you.
So, I invite you to start with our session.
Yeah, thank you. Thank you for this kind introduction. Uh, Before start of the lecture, just I wanted to clear that it should be the interactive session, not one-sided only. I am giving the continuous lecture and you are only listening mode, so that should not be there. So whenever you get the doubt or anything you are not able to catch, then you can just stop me. I will try to explain in details. Also try to have a one notepad or the notebook and pen and try to take the notes so that you will be in the sync with the lecture. Otherwise, if you keep only idle, then it will becomes boring. So try to have the notes as well so that you will not get the bored. And whenever you get the doubt, so you can just ask. Is it clear? Now I will switch off my camera to uh, spare some bandwidth for the our clear video, clear lecture. But anytime you can stop me and ask. Once I go in the presentation mode, so I will not able to see other participant. So you can just unmute yourself and try to ask the question. Okay. No response. At least yes, no, anything.
It's better when you unmute all students. If you would like to give feedback response, you need to unmute yourself, and instead of just putting thumbs up there, you can unmute yourself and show your attendance.
Sir, voice.
Sir, unmute yourself.
Sir, your
Okay, sorry. Actually, I was not knowing. That only I was saying actually once I go in the in second window presentation window, so I will not able to see the this either I am mute or whatever there. So you keep on saying anything you have the doubt or the if you are not getting sound or anything, so you can just stop me and ask to have that one. Okay, now can you see my screen now?
Yes, sir.
Okay, thank you. You can see the presentation, right?
Yes.
Okay, good. Okay, so as Vishal sir introduced myself, Dr. Mahendra Ghat, and I have completed PhD in the power electronics field. Then I joined in the Siemens, and from 2018, I am working here as a hardware architect and lead engineer for the many power electronics development in the Siemens, majorly for the applications like a electric vehicle charging system and the photovoltaic inverters. So that are the main areas where I'm working. Okay, moving to our today's lecture, I will just first have the some uh, connect to you to the topic by considering the what we are doing and what actually is power electronics and why we want to have the this power electronics in our subject, as well as the why we want to study the different type of the converters. So to get in touch, I will just start with the definition of power electronics. So power electronics, we can say it is this is the power electronics devices from converting one form of electric power into the another form of electric power. So the power electronics is the thing which has the devices which will convert the power from one form to the other form. So that is the whole about the power electronics. So here this picture can clearly say that what is the power electronics. So we have some form of the electric power, and we have some power electronics which will convert to the other form of electric power. So that is the overall, we can say the small definition of the power electronics. Now, if you go for the history of the power electronics, so power electronics has started in almost in 1882. So that time there was some discovery in terms of semiconductors. So from there, many discoveries or the many evaluations happened in the power electronics. And last major evaluation happened in it is in the 1990, where the IGBT was developed. Still, the power electronics is getting developed, but as a device point of view, there are not much we can say the change. But whatever the materials are used and the whatever already existing switches are there to improve the efficiency or the performance of that switches, then the whatever devices are there to improve their reliability, all that kind of things are still going on. And major now the changes are going on in the power electronics are the material used. So if you see previously there was the material called as the silicon material, but now new materials are coming like a silicon carbide, then the GaN, gallium nitride devices. So this has the devices are the have the more band gap actually, means they can operate at the higher switching frequency. So with the higher switching frequency, you will get require the more less any filtering and everything. So higher and higher frequencies are people going by using the different type of the material. So this type of the uh, evaluation or the we can say the developments are going into the power electronics, and this power electronics is still evolving field. There are many things are happening in the power electronics, not in terms of the devices only, but using that devices into the application and getting the more and more application. So that is the thing we are doing in the power electronics. Now, if we come as a power electronics, so we will not, if you are considering only power electronics, we will not restrict ourselves to the power electronics. If you are power electronics, then you should know all other things like a signal processing, analog and digital electronics, electromagnetics, power system, all that kind of things we require to have into the power electronics, because this power electronics is using all that kind of thing. So if we see the power electronics, so it is not only the switch, so the control of switch and the monitoring, conditioning, all that kind of things. Also, we are using some magnetics also in the power electronics. So when we go for this, so along with this power electronics, we will have all that kind of the disciplines in the power electronics. So this is a vast subject, we can say, power electronics, where which is the mix of all kind of disciplines in the one form. And as you go in deeper and deeper, you will be requiring the knowledge of all these type of the disciplines. Then coming to the why power electronics, or the what are the application of power electronics. So if you see, nowadays the power electronics is everywhere. It is getting misused everywhere. There is a no single area, we can say, which is out of power electronics, and the applications are still getting evolved. Is more and more applications are coming with a power electronics. What is the advantages of power electronics is we are trying to have the more and more efficient power conversion actually here. So if you consider the power electronics, we get the more and more, and also the controlled power. So that is the main advantages of having the power electronics. We get the controlled power with a very high efficiency. So that's why we can see the application, some of the application I have listed here. So you can see industries. So if you consider industry, in everywhere industry, the power electronics is getting used, like a processing equipment, welding, lighting, electroplating, pumps, compressor, induction heating, boiler, everywhere the power electronics is getting used. Home appliances, if you consider, which we are using now everywhere in refrigerator, vacuum cleaner, washing machines, dryer, mixer, everywhere the power electronics is again getting used. Commercial consideration, computers, electric fans, vending machine, audio amplifier, battery charger. So all these are using the power electronics. Medical also, all equipments now, whatever machineries are coming in the medical, so they are also using the power electronics. Automotive, so automotive is a where we now previously there was a very low use of power electronics in the automotive, but with a electric vehicle, nowadays the automotive also becoming a complete dependent on the power electronics. So these are the other also useful things where the power electronics is used, like regulators, radars, alarms. Aerospace is also using the power electronics. Satellite systems are using, aircrafts are using, all that kind of things are using the power electronics. Then transportation, motor drives, trains, trolleys, subways, locomotive, streetcars, elevator, magnetic leviators, all these are using the power electronics. Also in the telecommunication and major, again the power system is the different field, but there also now the power electronics is getting used in a larger scale, like a some of the application like a static circuit breaker, thyristor control reactor, harmonic suppression, HVDC systems, static var compensator, alternative energy sources like a wind, photovoltaic. So there also in major quantity the power electronics is getting used. The new fields are coming like a fuel cells, hydrogen fuel cell, some energy storage. So these are the some emerging areas where now there also the power electronics is getting used, right? Any doubt regarding the power electronics? You already started the studying, so you should knowing this thing, but I am just recapping this, where it is used and how is it working. Okay, now coming to the actual use of the power electronics. So how we can classify in the power electronics converters. So if you see the basic funda of the power electronics, we have the some source. So it can be the AC source or the DC source. Now, how you will get the DC source and that things already you studied. Like a one example of DC source is the photovoltaic inverter, photovoltaics, or the solar array. Solar array will give the DC output, and AC already we have the all the alternators which will generate the AC output. So we have the sources which are either AC or the DC. Now coming to the load, again we have the different types of the load. Like we have the AC loads as well as the DC load. AC load we can say the motor, induction motor. Induction motor is the AC load. But if we consider any your we can say the computer or anything refrigerator and everything, so all that equipments are running on the DC. So we have the DC load. So we have sources AC or DC, and we have load also AC or DC. Then why we require the power electronics? The power electronics is required because we cannot use directly AC to the DC, or if it has the DC, then we cannot use that to the AC. That is one thing. Also, if suppose we have the source also AC and load also AC, but if we want to control the load, like a one example is the induction motor. We have the induction motor and we want to control the speed of the induction motor. Then whatever AC we are getting, so that has to be controlled. To controlling that, again we require some kind of things which will convert that fixed source to the variable power so that we can control the load. So like that, even though if we have the AC source and the AC load, then also we require the power converter which will convert to the required uh, required form or the required power which can be controlled by the power electronics. So that is the beauty. We can use that to the if it is a AC source or the DC source, and if it is a AC load or the DC load. So whatever conversions are required, that can be done by the power electronics. So depending on these things, there are four type of the converters. One is the one if we have the AC input and we require the DC output, then it is called as the AC to DC converter. Then if we have the DC input and also we require the DC output, then it is called as the DC to DC converter. If we have the DC input and the AC output, then it is called as the DC to AC converter. Similarly, if AC input, AC output, then AC to AC converter. So these are the major four converters which we are using or which we have in the power electronics. And today we are majorly focusing on the this part, that is which has the DC input and we require the DC output, but at the controlled DC output. So where we will use the DC to DC converter. So this is our major main topic for the today's session. But other things also are there in the power electronics, and your sir will cover this all these things. And maybe already you have started, and some of the part you already covered. Okay, the same thing I have explained here. So there can be AC to DC converter, DC to DC converters, DC to AC converter, and AC to AC converter. Depending on this, there are different name like a rectifier. Rectifier we mainly use the naming when there is a input is AC and output is DC. That time we will say it is a rectifier. Inverter, it is inverting from DC to AC. That's why it is called as the inverter. You can remember the symbol also for the converter. We generally use that this type of the symbols when there is a rectifier. This is the AC, then it is converting to the DC. Similarly, it is a inverter. It is converting DC to the AC. So this is zigzag means AC and constant means DC. So that is called as the inverter. For DC-DC converter, majorly it is called as the chopper. So where it is convert to the DC to DC. Then the cyclo converter will convert AC to AC. So that is the particular name is given as a cyclo converter. Then the AC voltage regulator, it is again the AC to AC converter. So these are the different names are given, but the major four categories are like this only: AC to DC, DC to AC, DC DC, and AC to AC. So these are the four categories. Okay, so these are the power converters which we are using in our application. So all application will go around this converters only, for type of the major converters. Again, in that each converter there are many different topologies are there. Then different we can say the control or the how it is operating on that type. So there are different converter topologies, but the major grouping is in four groups only. Okay, but when we comes as a any converter, so there are a major these are the major components which we are using in the power electronics. So major components wise, we are using the semiconductor switches, and in semiconductor switches there are many switches, but majorly are using the diodes, MOSFETs, IGBTs, and SCR or the thyristor. So these are the main four MOSFET or the four semiconductor switches which are used. Again, these are different operation point of view. These are the it has the different operating range, like this diode. So diode don't have any control. So whenever there is a forward bias, so it will start the conducting, and whenever it is going in the reverse bias, so it stop conducting. Similarly, for the SCR, it it conducts only when it is in forward bias and the gate pulse is applied. But for the MOSFET, when we switch on the or we will give the gate pulse, it will start the conducting. If we stop the gate pulse, it stop the conducting. So it is a fully controlled, we can say. It is a uncontrolled. It is a semi-controlled. IGBT again fully controlled. So like that, different types of the switches are there, which we are using. Then our power electronics, any converter will not go alone with the this power electronics devices. It will have the some storage elements, and storage elements are mainly inductors and capacitors. So these are also we have to use in our power electronics converters, inductors and capacitor. Similarly, other components, like we require in some application the transformer. So some power converters are using the transformers. Even in the DC-DC converters also we use the transformer. So someone say that how we can use the transformer in the DC-DC converter. So there are converters for the DC-DC converter where how they will operate. First they will convert DC to a AC, then we'll have the transformer, then the transformer will operate on the AC to AC, and then again output of the transformer is converted to the DC. So if you consider the overall system, so like that, if I say, uh, just I will show you in the. So if we have, can you see my screen, right?
Yes, sir.
So this is our converter one. Just a minute. Oh, sorry. Okay. So here we have the here we can say this is the DC supply, and this is the some type of the power electronics converter which will convert to the AC supply and which will be applied to the transformer. Then again at the secondary of the transformer, we will have the again second converter which will convert this AC. So here it is a DC supply, here AC supply, then here we will get the AC supply, and here we will get the DC supply. So overall system wise, if you consider, so this is the DC-DC converter, but it is using the transformer in between. So like that, we use the transformer as well in our system. So that's why I have written as a transformer. Also the control circuit. So this is the major thing which we are using in the all power electronics, because whenever we have this type of the switches, so the gate pulses of this switch has to be controlled. And how we will control that? So as per our output requirement, we have to control this switch. So to control that switch, we require the control circuit. So by controlling control circuit, will decide the how these switches will be turned on and off, all that kind of thing. Of course, diode will not have the control, but other switches will have the control. And depending on the signal which you are giving to these two, it will control the output. So that's why we require the control circuit. So the complete system point of view, we'll have the at least this things. Transformer in some of the converters it is used, in some of the converters it will not use, but some of the devices, of course, it will be used in the all converters. Now, as we are using the two storage elements, that is the capacitor and inductor, I just have some slides to go through the basics of these capacitors, so that whatever now I am going to have the lectures, there I am using the basics of this capacitor and inductor. So just to have the brush up of your this basics, so I have considered these two. So we can say we are mainly using the capacitor and inductors are the storage elements. Then if we consider the capacitor, so capacitor is the acts as a like a voltage source. So whenever we consider as a capacitor, so it will acts as a voltage source. The fundamental circuit equation for the capacitor is the IC is equal to C dV by dt. So C is the capacitance, Vc is the voltage across the capacitance, and the change of voltage across the capacitance will use the capacitance current. So this is the basic equation which we are studying in the basics of electrical engineering. So that the same thing we have to use again and again for our derivation. And the energy stored in the capacitor is the 1 of CV square. So only thing we have to remember is that capacitance is always tends to behave like a voltage source. Similarly, for the inductor, it will behave as the state variable is a current, and it will behave as a current source. The voltage across the inductor is L di by dt. So L is the inductance, IL is the inductor current through the inductor, and whatever change in the current is there, so that will give the voltage across the inductor. And this is acting as a current source, and the stored in the energy in the inductor is a 1 half Li square. Clear? So these are the basics. So just brush up. Okay. Now again, some of the things we have to remember for the whenever we consider the any power electronics converter. So this is also the basics, but just to apply to the power electronics, as I said earlier, the capacitors are the constant voltage source, and whenever there is a constant voltage source, we never connect the switch in the parallel. Why we don't connect the switch across in the parallel with the capacitor? So again, I will go to the uh, tab. So if I show you, so if I consider this thing, so this is the your capacitor, say. So this is your capacitor, and if I connect the switch parallel to this capacitor, okay, so I have represented a small ideal switch which can turn on and turn off. So this is the switch. If I connect this circuit, and when I switch on this switch, so if I switch on this switch, so it gets shorted here. So what is happening here? So this is the inductor. This is the already charged to the some value of Vc. So that Vc acting as a voltage source, you are directly shorting through this thing. So you are shorting the capacitor. So that's why we cannot connect any switch directly parallel to the this voltage. Okay. Similarly, if we have the inductor, and if we want to connect in the series, okay, so there is a very high inductor is there, and you have already switched on the switch. So what is happening? The current is flowing through the this, and as you know, the inductor will try to oppose the change in current. So when you start the opening this switch, so what will happen? Whatever voltage applied here plus voltage across this, you are trying to change the current through this with a very high value. So di by dt is very high because you are interrupting the current. So di by dt is very high, and the voltage across this is very high, and all this both the voltages will get applied across this switch. So there are two basics fundas. We cannot connect the switch parallel to the voltage source or the capacitor, and we cannot connect the our power electronics device in series with the inductor or the, we can say, the current source. So these things we have to remember always in our circuitry. Then one more thing is that in steady state, whatever capacitors are there or the inductors are there, so in steady state there will not be any energy stored in the steady state. So in transient, maybe there will be the plus minus energy, but when we go for the steady energy, so whatever energy you are storing, the same energy will be given back. In steady state, the energy stored in it will remain the same. It will not change. So we can say whatever input you are giving to that storage element equals to the output. So that is the so our these are all our basics actually, which we have to follow in the power electronics. So that's the what I want to just give. So this was the basic. Any doubt in the basics, whatever I have shown you?
No, sir.
Okay, so these were the all basic already you have covered, and we are using that basics in our power electronics. That's why I just brushed up it. And with that, I will be directly going to the our main session, that is the DC to DC converter. It is also called as the chopper. So this is our main session, today's session, and we will start to the this session with the basics, which I have just now you explained. Okay, so DC to DC converter. As I said, why we require the DC-DC converter? So DC-DC converter has the input of DC as well as the output of DC. But we require the DC-DC converter because we want to convert the fixed DC to the variable DC. Say I have the DC source of 10 volt, but I have one application or the uh, one device which is operating at the 5 volt DC. So in that case, what I have to do? I have to convert that 10 volt to the 5 volt. Okay, so there it can be converted by the other ways also. Like one of the way is that here I have we can see. So this is the 9 volt battery we have, and we have the load which will require the 3 volt. So this can be achieved by adding the some resistance here. If the resistance of RL load is RL, then if we add the 2 RL and if we apply the KCL, then you can see that you will get the 3 volt here. But what is the problem here? Whatever we require the 3 volt, we have the 9 volt, and how we have achieved this? This we have achieved through the by doing the some drop here. So 6 volt of drop we are doing through the resistor. So whenever there is a drop, whatever I square R, whatever current, because it is flowing through the this and it has the resistance, that is the I square R will be the losses. So what we are doing, we are getting the 3 volt by doing the some loss in this resistance. So by achieving this variable voltage here, so this is the lossy solution. So this is the one solution, but this is the lossy solution. Similarly, there is a one called as the linear regulator. So this linear regulator is again, this is a power electronic switch, but it is not operating in the saturation mode. So that's why again it has the like a variable resistance. So by operating this variable resistance, you can control the output of this one. But again, this is also like a acting as a variable resistor, so it is a lossy component. So by adjusting transistor base current, the output voltage may be controlled over range of 0 to whatever input voltage. But the power loss in the transistor makes this is circuit again inefficient. So these are the two solutions which already had in the past with a lossy thing. So that's why nowadays these solutions have not particularly used in the power electronics. We have the good solution which will not have the any loss. There will be the small loss, but very low loss as compared to the this kind of the devices. Okay, now uh, just whatever I was saying. So if I operate like this, say if I want to have the a switch, a efficient means linear regulator, if we want to operate it efficiently, so what will happen? We will completely either turn on or turn off the switch. So what will happen? Either it will get turned on or the off. There will not be any loss in this switch. So when it is turned on, so what will happen? It will get connected to the this. So you will get the whatever Vs voltage is there. So that will be getting applied across the VO or the load. So here you will get the Vs. So this is the waveform you are getting when this switch is closed. Now if I open completely this switch, so there is no path to flow the current. So what is happening? There will not be any voltage applied across this one. Okay. So this is the closed position and this is the open position. So for with this, whatever happening, so for DT time, I am switching on this switch, and for remaining time, I am switching off this switch. So it is turned on switch for the this or the close switch for the DT time. D we will take as a constant which will vary from between the 0 to 1. Okay. So whatever time period. So this is the time period where we are operating either in switch on or switch off position, and out of that, say for the 0.5. So D is equal to 0.5 means for the half of the time I am turning on the switch and half of the time I am turning off the switch. So if I do like this, what will happen? What output voltage you will get? Output voltage, obviously it will be the uh, uh, integration of the integration of this time. Over this time, if we integrate, you will get the output voltage. So the output voltage I can say is integration over the time, that is the 1 upon T, integration of 0 to T, and whatever VO of T dt you are getting. So VO of T, you are getting what you are getting? You are getting the Vs for the dt time and 0 for the dt to T time. That is the 1 minus dt time. So the same thing I have done, 1 by T, 0 to dt, Vs dt. Vs because for this time we have the Vs, and for this time it is a 0, so plus part you can ignore. So what you will get, if we integrate this, you will get the Vs into D. So this is the output voltage. So the simply switching on and switching off, you will get the output voltage which is equal to Vs by D. Now if I change D value, say first I will keep D is equal to 0. So what is the output? If I keep the D is equal to 0, VO is equal to Vs into D is 0. So you'll get the 0 output. Similarly, if I keep D is equal to 1, you will get the output voltage as Vs. Vs is our input voltage. So if D is equal to 1, then you will get the complete input voltage to the output voltage. If I keep the 0.5, you can see the output voltage is the half of the input voltage. Similarly, by varying between the 0 to 1, you will get the all values of output voltage with respect to the input voltage. Okay. Now, how you will control the D? So to controlling the D, so what is D? D, if you see here, here you can see this is the time of T on. T on is the time where the switch is closed or the switch is on, and T off is the time when the switch is open. So if it is open, it is called as T off, time for the time for which the switch is off, and the time for which switch is on is called as the T on. So if you consider that, then the D you can write as the this is the we can say D is equal to our on time divided by the complete time. Complete time is nothing but T on plus T off, or you can say the T, and T on D is equal to T on by T. So we can say T on by T, T 1 by T is nothing but the F. F is the frequency. So we can say T will come as a T on into F. And we want to change this D. So we can change this D either by changing the T on time or the frequency time or the both. So to control the output voltage from this uh, uh, diagram, we can say we have to control the D, and to control the D, either we can control the D on time or we can control the frequency. So if we control the frequency, if I increase the frequency, what will happen? The D value get increased. If I reduce the frequency, the D will get reduced. And once I change the value, so the output voltage is getting changed. So by changing the frequency, we can change the output voltage. Similarly, by changing the T on, if I change the T on time from 0 to T value, you will get the D value from the 0 to 1, and the output voltage varies between the 0 to input voltage, that is the Vs. So that is the two uh, control methods used to control the DC-DC converters, called as the frequency control and on-time control. Clear?
Yes, sir.
Okay. So instead of this, just I have shown here the same example. 9-volt input is there, and I want to have the output voltage of 3 volt. So instead of using this resistance, what I will use? I will use the power electronic switch, and I will try to get the 3 volt. Okay. So my value should be 3 volt. Average value should be the 3 volt from the input voltage of 9 volt. So if I want to have that one, so what I will do, I will switch on this switch for the 1/3 of the timing. So whatever complete timing is there, if I switch on this switch to the 1/3 timing, so the same thing I have done 0 to T third. So 1/3 timing only I switched on, and the input voltage is 9 dt. So if you solve this equation, so what you are getting is the output of 3 volt. So without any loss, I got this output, because here either turning on. So if you consider the idle switch here, there will not be any loss or any resistance of this switch. So all 9 volt will get applied across the output voltage, and when there is a open, so there is no voltage is getting applied across the output. And if I keep this switch on for the 1/3 of the timing, total time, I will get the 3 volt without any doing the loss. Okay. And as we derived the equation, so how we will control the output? So there are mainly two methods. One is the constant frequency control or the on-time control, and other one is the variable frequency. Because to control the output voltage, we have to control the D, and D is nothing but T on into F. So either we can control the T on or the control the frequency. So here we can see the example. So what will happen if we change this T on So here you can see the lower T on. Here the frequency is the same, but T on time has increased. So out of total timing, we have changed the T on. So if you do this, whatever average value, if you consider the average value here, so it will be lower. But now the T on is higher for the higher timing, so you'll get the higher average value. So again, so here you will control that with by controlling the T on. Okay. Similarly, we can also control the output voltage by controlling the frequency. So this is the one example. We are keeping the T on time fixed, but we are changing the frequency. So what is happening? So T on will remain the same, but the as we change the frequency, so the total time has reduced here. So the whatever average now again you are taking. So here average you have to add this plus this and take the average over the whole period. Now only you have to take the average this per time plus this time only. So you will get the higher average. Okay, so that's why we by changing the this load, sorry frequency, we can change the load. Again, output voltage. So again in this there are two methods. We can keep the T on time constant and vary the total time, so the T off will get vary, or we can keep the T off time constant and vary the T on time. So again, how vary the frequency, so the T on get vary, and you will get the same result. Okay, so these are the different control, and as per the input, I think you have already did some experiment on this one, like a on-time control and the frequency control to control the output voltage for the DC-DC converter, right? But why and how it is happening? So that I have just tried to clear here. Till now, everything is understood, or any doubts are there?
No, sir.
Okay. If you have any doubts, you can just ask, or anything you feel that I didn't understand or anything, you can just ask me. Again, I will try to explain it.
Sir, will you please explain the numerical once again?
This one or previous one? This one.
No, that one only.
Okay, here. Okay. Okay. So here you can see, Miss, I want to get the 9 volt, and 9 volt input is there, and output we want as a 3 volt. Okay. Now, if we consider the, we adjust the RL, RL is the already it is there, but if we add the 2 RL here, so what will happens? Voltage across this will be the twice of this voltage. Means here you will get the twice of the whatever input voltage. That will be 2/3 of this voltage will get applied across here, and remaining 1/3 will get applied across here. Right? Voltage divider. Direct. It is a simple voltage divider. As it is a 2 RL, you will get the 2/3 of the voltage here and 1/3 of voltage here. So here you will get the 6 volt, and remaining 3 volt is there. But what is happening here, even though we are applying this resistor in circuit, so whatever load requires, suppose I want a X amount of current, so that has to flow here. And by adding this resistor, that the same current will flow through this resistor. And that I square R losses we are increasing. So instead of that, same thing if I want to get, I can get with this switch. So this switch either it is in closed position or the open position. Now when we are in closed position, means whatever input voltage is there, that complete voltage is getting applied across this. And when there is a this switch is open, there is no voltage is getting applied across this. But finally, if we consider the voltage across this, so this type of the voltage we are getting across the output. Means sometimes we are getting the 9 volt and sometimes we are getting the 0 volt. So this type of things we are getting. But here, whatever voltage you are getting across the load, that is the actually average of this actually. because we are not getting constant voltage, so we cannot set the 9 volt is completely always is getting applied or the 0 voltage applied, but it is a average. Average means what? Integration of the over the period. So integration of over the period means we can integrate from the 0 to t of this circuit or this waveform. Okay, so if I did that, only 1 upon t is the total time integration from 0 to t and whatever voltage we are applying for this period vx dt. Now what we are doing, as we want a 3 volt, and just I have miss we can vary this to a different type, but we want 3 volt. That's why I kept this to the 1/3 of the timing. So if I integrate this, so 1 upon t, 0 to t by 3, 9 whole dt plus again 1 upon t from t to t, t by 3 to t, there is a 0 volt. So this is the 0 dt. So if we integrate this and multiply by 0, this term is coming as a 0 volt only. And for this term, integration of this 9 is constant. So you can say 9 by t, and integration of dt is the t over the limit of t by 3 to 0. So I will just shift to the my this one. So here what is happening? So remaining thing is 1 upon t, 0 to t by 3, 9 dt, right? So what it will give? This 9 constant, I have taken the outside, which is the constant, by t. Integration of dt is the t, small t, over the period of or the limit of t by 3 to 0. So if I put this value, what you will get? 9 by t into this t is t by 3 minus 0. I will ignore that 0. This t will get cancelled, and this is the 3. So you are getting the output voltage as a 3, right? Clear?
Yes, sir. Sir, actually, my doubt was that the T by 3 value you have taken it because the input is 9 volts and output is 3 volts.
Yes.
For that, you have taken T by 3, na?
Yes.
So we can change it according to the values of voltage.
Yes. If you want to the 6 volt here, say, then it will be the 2t by 3. On time will be the for the 2t by 3. If you want the
Okay, okay.
6 volt at the output. So by controlling this, you can get the any voltage. But just I have given this example because we are referring to the this example actually. So the same thing, if we want to achieve, then we can do like this without any loss. So with this, we are, if we want to have this type of the, here it is a fix again, but here by varying the t time on t on time, you can vary get the any value. So just one example is, if we have the t by 3, then you will get the 3 volt. Similarly, 2 t by 3 on time, you will get the 6 volt. Clear?
Yes, sir.
Okay. Now coming to the actual converter. So there are different types of the DC-DC converters. So the basics I have just explained, and how we can control the DC-DC converter. But there are many DC-DC converters which are broadly classified into the two main categories actually. One is called as the isolated DC-DC converter, and other one is the non-isolated DC-DC converter. Isolated DC-DC converters are the converter which will have the isolation. Isolation, how you will get the isolation? By having the transformer in between. So any DC-DC converter which is using the transformer in between is called as the isolated DC-DC converter, and which I have just start of the this I have just explained how transformer can be used in the DC-DC converter. So that type of the converters is called as the isolated DC-DC converters, and other where the transformer is not used, where there is no isolation between the input voltage and output voltage. Of course, there is a control, but there is a no isolation. As such, there is electric isolation is not there. Direct you are connecting, or the input is getting connected to the output, and or the you are isolating or the switching off the switch and turning off the voltage. So that type of the converter is called as the non-isolated converters, non-isolated DC-DC converter. Again, this isolated or the non-isolated have the different types, called as the step up converter, step down converter, and step up step down converter. Step up converter is called as the buck converter. Buck means you are step down converter is called as the buck converter. Step down means what is there? Whatever output voltage is there, so that is the lower than the input voltage. Similar, whatever terminology we are using in the transformer, step up transformer or step down transformer, same thing we are using in the DC-DC converter. If output voltage is lower than the input voltage, always you are getting the lower input voltage, lower output voltage than the input voltage, then this converter is called as the step down converter. Also, it is called as the buck converter. Okay. If the output voltage is greater than the input voltage, which is also possible in the DC-DC converter, is called as the step up converter. Okay, so there you are getting the output voltage which is higher than the input voltage, equals to or the higher than. It is called as the step up voltage, step up converter, and it is also called as the boost converter. So buck converter, step down converter, where the output voltage is getting stepping down than the input voltage. Boost converter is step up converter, where the output voltage is more than the input voltage. There is also one type of the converter is step up step down converter. It will have the both functionality. Either you will get the output voltage which is lower than the input voltage, or you will get the output voltage which is higher than the input voltage. So there you are getting the step up option as well, and step down also, depending on the D value. How you will get the step up step down, so that will will in the next some of the lectures, so that we can cover. So these are the three basics. First two categories. One is the step isolated converters, non-isolated converters, and again all in isolated as well as the non-isolated. You will have the step up, step down, step up, step down. So these are the three basic things which we are getting. In one of the converter, step down converter is the buck converter, which is commonly used, which I am taking here. There are other converters also for the step down, but the buck converter is commonly used for the stepping down the output voltage. So that is the first converter which we are starting here. So this is the overall buck converter looks like. So the buck converter has the many devices. This is the input voltage or the input source, we can say. This is our load where we want to control the output voltage, VO. So Vs is the input voltage, VO is the output voltage. To getting this in buck converter, it uses the one controlled switch. So it can be either IGBT or the MOSFET. It can use the thyristor, but if we are using the thyristor, so there is no turn off capability for the thyristor. You already studied the thyristor. So you can switch on the thyristor, and we have the DC. So we can, it will be always in the forward bias. So you can switch on the thyristor, but you cannot get the natural commutation for the thyristor. You require the force commutation to turn off the thyristor. So nowadays, means in almost all application where the DC-DC converters are used, either IGBTs or MOSFETs are used for the this controlled switch, because it will have the control. Whenever you are giving the get pulse, it is getting turned on, and whenever you are removing the get pulse, it is getting turned on to the MOSFET and IGBT. So this one semiconductor controlled semiconductor switch is used here. One diode, which is uncontrolled, is used. Inductor, this is the storage. Again, the capacitor, this is also the storage, but it acts as a filter to get the output voltage. So this is the overall basics or the block diagram of the buck converter or the step down converter. Now the operation of this buck converter, how it will operate and how we will control, so that I will explain in the some next lecture. But before that, do you want have any small break or should we continue? 5 minutes break. Okay. No response means should I take it as a yes or no? I don't know. Yes, please. Anyone? Don't worry. 5 minutes break is not an issue with your sir as well, if you want. But no one is answering, so I will continue. Or should I? Should we? Okay, then I will
Yes,
continue.
5 minutes. Hello.
Yes.
Yes, sir. 5 minutes break.
Okay. So it's 8:05. So we'll meet at the 8:10.
Sure, sir.
Okay.
You all should join again at 8:10. I'm keeping it on hold and the recording is going on. Nobody, you can put it on hold as well. So attendance can be downloaded. Now I will download the attendance.
Hello, I'm back.
Yes, sir. We can continue now.
Okay, okay. Uh, okay. So as I said, uh, this is the buck converter where we will have the major components is the one switch. Just I will take the pointer. So this is the switch, diode, inductor, capacitor. So these are the major components which we will have. Now just try to get the understanding of the working of this buck converter, how it will work. Okay, so there are two state of this switch. One is when it is getting turned on and turned off. So when it is turned off, this will get short circuit, and when it is turned off, it is getting open. Now when first condition, we can say the when switch is on or the switch is turned on. So what is happening? This you are getting the short circuit. So if you see the voltage, this voltage is getting applied directly to the load. So this is the path which is getting completed. So the current is flowing through the inductor and it is going to the output and returning back to the source. So what will happen? So the inductor current will start the increasing as you have applied the, you will not get the constant current here to the inductor, because the inductor will try to the increase have the ramp in the your in your for the current. So when switch is off, the inductor is current is getting increased and the current path is like this. Okay, now when switch is off, so this you are getting turned off, so there is no connection between this to this. But as the inductor current is there and it will not directly go to the zero, even though you have isolated this source by turning off this switch, the current will not go to the zero, or it will not interruptly go uh, to the zero value. But what it will do, it will either remain the constant to that value, or if anything loading is there, then it will try to reduce it with a slope. Okay, now we have the, this is the current and we have the already the current flowing through the inductor and this is the load. So what will happen once you turn off this switch, whatever this current is there, it will try to flow through the this diode. So you will get the path like this. It is called as the freewheeling. So there is no source connected to the load, but the current is getting freewheeled through the this diode. So that's why it is called as the freewheeling system. But as the inductor is there and the loading is there, so you will get the a decreasing current here. Okay, again at this instant, so I have turned on the uh, switch here at this instant and turn off switch at this instant. And again after t time, again when switch is turned on again, so what will happen? Again the inductor current will start increasing. So you will get the this current, and when it switches off, again it will start the decreasing, that is the freewheeling. So you will get the this inductor current here. Okay, now how this diode is getting forward bias? See, first when we are applying the source, so it is getting the, we have the L, VL is equal to L di by dt. So we are trying to force the increase the current. So di by dt is positive. So we can say we are getting the plus and minus here. Okay, so that's why the current is positive and you are getting the VL is, which has the polarity of plus and minus. Okay, now when switch is off, what is happening? You are trying to reduce the current now. So even though current is positive, but whatever di by dt, because your VL is equal to L into di by dt, right? So this is our basic equation for the voltage across this. At first stage, what is happening? We are trying this di by dt to increase. That is the positive di by dt. So that's why you are getting the positive voltage, that is the plus here and minus here across the inductor. And at the same time, what is happening? Plus is getting applied the across this switch, and minus diode, and minus is getting applied the this one, cathode and anode. So what is happening? This is in reverse bias, so this will not conduct. Only we have the path this one, and the voltage getting generated across the inductor is plus and minus. Now when this switch is off, what happening? The current is trying to decrease. Means this term is become negative. Okay, so this is becoming negative term. This is the minus term now. So when it is become negative, you can say this is the minus and this is the plus. So what is happening? Minus is getting applied across the this terminal of the diode, and this plus is getting through the load to the this one. So what will happen? It is automatically coming in the forward bias and start the conducting. So your current will start flowing through the this path through the diode. So for this, we can say whenever there is a switch on, so the current will flow from the source to the load through, and the diode is reverse bias. And when switch is off, the current will try to freewheel through the diode as the diode is getting forward bias, because this voltage is getting negative polarity across the inductor, and that is getting applied across the diode, which will convert that diode to the forward bias, and it will start the conducting. So this is the overall phenomena for the buck converter when for the current point of view. Now how you are getting the voltage at the voltage output voltage you are getting, so that equation we will derive for the output voltage. But for the current point of view or the operation point of view, when switch is on, the current is getting increased, you will get the polarity as plus minus here. And when the switch is off, the current is trying to decrease and the polarity is minus plus, which will forward bias the diode, and it will freewheel this one. So this is the overall operation of the buck converter. Okay, now we got the function of the this switch, function of this inductor, then function of the diode. Only the capacitor function is remaining, so that we will come into the some of the coming lecture, or the some of the uh, in shortly actually. Okay, why you are using this capacitor. Other components wise we already clear, why we require this switch, why we require inductor, and why we require the diode. Okay, now to derive the equation of this buck converter, we will again do the some assumption that the inductor current is periodic. Periodic means what? After the periodic means the after the t time, whatever initial state was there, the same state you are getting after the t time. Means if the inductor is increased to this one, so after t you will get the same level of the inductor value. Again it is increasing and to coming to the same level. So that is the called as the periodic. So IL of this is the your t, then 2t. So if it is this, we are considering as a periodic. So our inductor current is periodic. So that is one assumption we are doing. The average inductor voltage is zero. Means the voltage across the inductor over the time of t. Means if we divide into the t on and t off, and if we take the average over the time, then the average inductor voltage is zero, which should be, and the average capacitance current is zero. So for as it is a inductor is the current source, we can say the voltage across that average voltage average inductor voltage is zero, and the current, it is a voltage source, we will say the average current is zero for this one. The power supplied by the source means what? PS we can say, which will be equal to the power supplied to the load. That is the PO. This is the ideal case. Non-ideal case will be there will be some losses. There will not be zero losses, but there will be some losses. So we can say the output power, input power equals to output power plus the losses. So this is the non-ideal condition, and the ideal condition we will consider as a input power equals to the output power. So these are the some assumption we will do for the our derivations. Then so again some of the assumption is that, see, if I keep the off time very low and if my on time is very high, so in this case what is happening, you can see first when there is a switch is on, the inductor is current is getting to the some value. When switch is off, it is getting reduced, but it has not reached to the initial value. Okay, so it is a not periodic. So in that case, again if you switch on the switch, so again it will start, inductor start increasing, and when switch off, it will go to the this value. So in any of the case, it will not come to the our initial value. So that's why it is a unstable current. So what is happening here, you can see the current, inductor current is again and again getting increased here. So that is the unstable case. Then decaying current is means, in this case what is happening, suppose the start current is this one, we switched on the switch and the current reached to this, but the switching off is for the longer time. Then what is happening, it is going below the initial stage. It was the initial stage and now it reached to this one. Again you switch on and switch off, then you will get the to the this range. So in that this way what is happening, it is going to the zero value. So this is called as the decaying current. In some cases we have to go for the decaying current and also for the increasing current, but in steady state we will have the this stage. So in steady state always whatever initial state of current is there, so we will be after t time we are reaching to the that same value. So same value increasing again decreasing to the same value. So this is the our steady state value. And in transient you will get the this two, but in steady state you will get the this one. So the same thing I have noted here. The circuit is operating in steady state. So finally we have to operate in the steady state operation. The inductor current is continuous, always positive. Means if we see here, the current is going in all three cases, it is shown as the always positive. But is it possible that the inductor can go to the zero value? So if I start from the zero and if I turn off, and second turn off is at this instant. So from this instant to this instant, you will not have the current because already it is reached to the zero. Okay. So this also the state is there, but in our derivation, we will consider as a inductor current is the continuous, means this current we will consider. The capacitor is very large and the output voltage is held constant. So the capacitor, whatever ripples are there, so that will be absorbed by the capacitor and you will get the constant output voltage. So that also assumption we will do in our derivation, but ideally it will not be there. So if we consider the non-ideality, you can derive for this as well. The switching period is T, so which already we consider. The switch is closed for the time dt. T on time is dt. T varies between the 0 to 1, and 0 to 1 into T is the on time, and open for the time is 1 minus d into T. That is the T off time. And the components are, again we will first consider the idle components. Okay, so these are the some of the assumption we will make, and with that assumption we can say we can derive the equation. But again, before going to the equation, so I will just introduce what is the continuous and discontinuous conduction. So it will depends on the inductor current. So if inductor current is always positive, it is not reaching to the zero, so it is called as the continuous conduction. Here you can see it is starting from this point, then it is going to the higher value, again coming to the to the previous initial value. Similarly, at this point, initial value, but none of the case it has reached to the zero. So it is always positive and greater than the zero. So this case is called as the continuous conduction. Again, this is the inductor current, but always it is a positive. It is called as the continuous conduction. Again, this is the delta I out. Delta I out is the difference between the I max maximum value and the minimum value. So this is the delta I out, you will say, and this is the average I out. Even though you are getting the current is this, but actual value which you are getting at the output is the this average value. So this will call it as a I out. Now, if I say in some cases it is happening that it is just reaching to the zero, and at the same instant if you are turning on the switch, so it is called as the critical conduction. So here it is just reaching to the zero and we are switching on the switch, so it will start again increasing. So it is called as the critical conduction. The second one more case is that it is already reached to the zero, still we have not turned on the switch. In that case, for some times there will not be any current through the inductor, and after some times you are turning on, that time it will start the increasing. So this is called as the discontinuous conduction. Again, for our derivation and everything, we will consider this case, that is the continuous conduction mode, and our whatever derivation I am deriving, that will be applied to the this continuous conduction only. Okay, coming back to the our converter. So I explained either the switch is turned on and or the switch is turned off. So the first case is the when switch is turned on. So when we switch on the turn on, so what is the equivalent circuit? You can see this source is getting shorted here through the inductor and the load. And as this voltage, whatever input voltage is there, so that is getting applied across the diode, which will reverse bias the diode, and you will get the open here. So this is the overall circuit for the when switch is turned on. Now, if I apply this for this condition, if I apply the uh, Kirchhoff's voltage law, KVL, so what will you will get this voltage, this voltage. If I say this, if I apply the KVL here, what is you are getting? Vs. Okay, I will start from this. Okay, so the polarity of this is the plus minus, so we can say minus VL. Okay, minus VO equals to 0. So I have just applied the Kirchhoff's voltage law for the whole circuit like this, Vs, VL and VO. So this is there. So if I just simplify it, I can say VL is equal to Vs minus VO, right? So just I have taken the VL on this side. You will get the Vs minus VO. So this is the VL. VL is equal to Vs minus VO. And we know VL is nothing but LdIL by dt, where L is the inductance of this inductor and IL is the current through the inductor. So depending on this, you can say DIL by dt. If I simplify this, if I take this L on this side, what I will get? DIL by dt is equal to Vs minus VO, this term divided by L. Okay, and this DIL by dt means what? When the switch is closed, so the current is going from the this value to this value. Okay, and this is nothing but the this minimum value to the maximum value. I mean to I max, and which is nothing but we have called as the delta IL. So delta IL of close is equal to Vs minus VO into L, where what I did this dt, just I will here one more step is there where I am writing as a DIL equals to Vs minus Vo divided by L into dt. Okay, so dt I have taken on this side. So you will get the delta IL is equal to Vs minus Vo by L into dt. Now if I integrate this both sides, okay, so integration of delta IL will be the from this value to this value it is going. So I will say whatever the delta IL is there when switch is closed is equal to integration of this term, and this term, this is the Vs minus Vo L is constant, and integration of dt is nothing but integration from the 0 to dt. Okay, so which is nothing but the dt, because we are getting the uh, voltage across the inductor when this is getting applied, and this you are not getting applied. So this is the dt, and this is the t. So the current through the inductor, if I consider voltage across the inductor is the, as I shown you, this is nothing but Vs minus Vo divided by L into dt. So integration of this dt. So we are just considering this time when the current is increasing, which is nothing but the delta IL close is Vs minus Vo into L into dt. 0 to dt we have integrated. Okay, so this equation you will get when switch is closed. When switch is closed, you will get the Vs minus Vo by L into dt. Similarly, when switch is off, similar thing we can do when switch is off here. So what is happening? Now the diode is getting forward bias and the switch is open. So this is the path you are getting. Now in this case, if I calculate the VL, so this is the KVL you have to apply for this one. So what is happening? So VL is equal to minus VO you are getting. So VL is equal to minus VO. Okay. And again, VL is nothing but L DIL by dt. Again, I did the L on this side. So it is getting the minus VO by L. Again, I will take this dt on this side and integrate it. So what I will get? Delta IL open, which is equal to integration of minus VO by L into dt. So integration of dt is there, but now time is from integration is from dt, because already t on time is over, t of time is dt to t. So integration is this one. So integration of dt over the time of dt to t. So if I simplify this one, what I will get? This term minus VO by L as it is, and integration of dt is t over the limits of dt and t. So if I put this value, it will becomes the t minus dt. So if I take the t common, I can say 1 minus d into t. So you are getting the equation when switch is closed as a for the delta IL open is equal to minus VO by L into 1 minus d into t. So these are the two equations we have derived when switch is on and switch is off. Now, as we said, the inductor. Okay, so inductor is getting turned on and turned off, and we are considering the steady states. So what is happening? Whatever I mean is equal to I mean, the same I mean I will get the after the t time. This is the periodic and steady state we are considering, and this is the delta IL. So whenever whatever delta IL is for the on time is there, the same delta IL you are getting at the off time. Or we can say delta IL, whatever change in the delta IL is there for the on time and change in the delta IL for the off time, if we add both, will gives the zero value. Okay, So I use the delta IL close plus delta IL open is equal to 0, and whatever equation we got. So if I put that equation in this, so for the delta IL close, I got the Vs minus Vo by L into dt, and for delta IL open minus Vo by L 1 minus d into t is equal to 0. Now if you simplify this equation, so what is happening? So this L is already getting cancelled. Okay, so Vs dt minus Vo dt minus Vo 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 t and plus Vo dt. So Vo dt terms will get cancelled. So here I will just try to simplify. Vs into dt, then minus Vo into dt, then minus Vo t Vo t, then plus Vo dt, which is equal to 0. So you can see these terms are getting cancelled. So this and these terms are getting cancelled. Then I can remove the t from this, and if I simplify this, you will get the Vo, this term. If I take on this side, right hand side, Vo is equal to right Vs into t. Okay, so output voltage is equal to input voltage into the d, which we wanted to have to the control. So to get the buck converter, whatever buck converter are there, so we are getting the whatever equation we want with the operation of the buck converter. So this is the equation we got for the buck converter. By varying the d, you will get the output voltage as a Vo. Okay, and here you can see, as I already said, d will be varying between the 0 to 1. So when d is equal to 0, what is the output voltage? Output voltage equals to Vs into 0, which is equal to 0. And when d is equal to 1, so the output voltage is Vs, which is the input voltage. So what is, and d is in between that 0 to 1, you will get the output voltage between the 0 to Vs. So always here you are seeing, you can see it is either equals to or the less than the input voltage. Okay, equals to or the less than. So that's why the output voltage is lower than the input voltage or the equal. So that's why it is called as the step down converter or the buck converter. So this equation also you can find by using the this simplified equation, which is by just writing the VL for the on time and off time. So what is the VL at the on time, which is the voltage across into dt, plus at the off time, this is the voltage across, and the addition of the voltage across the inductor. As I said, over the cycle, the voltage across the inductor will be equals to the 0. So if you simplify this equation also, you will get this also, or whatever method I have explained to you. So that also method you can use to derive this output voltage equation. Some of the other equation you can derive. So for the our buck converter, the average inductor current, so IL, which will be equals to the IR, because the same current will flow through the inductor current, whatever inductor current is there, here inductor and the load. So this is the circuit. Either it will come from the source or the through diode, but whatever inductor current is there, the same current will flow through the your load. So the IL average is equal to IR, which is nothing but a whatever resistance R is there here, R is there, and output voltage VO by R. So this you can consider as a average inductor current. I max, now the inductor current is this one, and this is your average inductor current IL, and this is the I mean, and this is the I max. Okay, so I max value, how you will get whatever average current is there. If we add in this, which is this total is the delta IL. Okay, so if we add the half of the delta IL, you will get the, in the average value, you will get the I max, which is IL plus delta IL by 2. And if we subtract the half of the delta IL, you will get the I mean. So this is this value. The same equation you can see, IL plus delta IL by 2 is the I max, and IL minus delta IL by 2 is the I mean. Now if I put the whatever equations I got, IL average current VO by R plus delta IL by 2, IL delta IL is nothing but VO by L into 1 minus dt. So that we derived. So that value I have put it here. So if you put that value, you will get this equation. VO is equal to 1 by R plus 1 minus D into 2LF. F is the T is taken as a F, so you will get this equation. Similarly, for the I mean, you will get this equation. So if you know what output current you want, and if you have the inductor, if you choose the inductor, and if you know at what switching frequency you are operating, then you can calculate the what will be the ripple. So what is the maximum ripple you are getting, and what is the minimum value of the ripple you are getting in your current. Okay. So here the same thing they have written. Now if I want to control this delta IL, okay, so if I want to control that delta IF, so I have to change the L and F so that my I max and I mean will remains within the limit. And to get that one, what I will do, I will just equate the above equation can be used to determine the combination of L and F that will result the continuous current. Why continuous current? Means I will choose the inductor value such that it will be always in continuous conduction. Means it should not go to the zero. So if I say this is my just the touching current. So if I try, this is the minimum value. So if I equate this to the zero, okay, so that way means if I keeping the L value such that it is just reaching to the zero, it will give that critical value. But if I increase the L value above that, so it will not reach to that one because it is a inversely proportional. L, if you see here for the I minimum is zero, means it is a critical conduction. Okay. And if I increase this LF value, what will happen? Your I min will not go to the zero. So to get this critical value, I just did I min equals to zero. So if I equate this equation to the zero, I will get this term, which is the minimum term required to get the continuous conduction, because I want to operate always in the continuous conduction. So simplifying this, if I take the frequency here, so this will give the L minimum. So this is the 1 minus D into R divided by 2F. So I can say if my inductance value for this switching frequency is greater than this L minimum value, then I can say my converter is always operating in the continuous conduction. But if this value is lower than this, means what? I am reaching to the zero well before this one, and for sometimes I will remain to the zero and I will operate in the discontinuous conduction. So I will say this is the my critical value. Above that inductance value, my converter will operate in the continuous conduction. At this value, it will operate at the critical conduction, and below this value, it will be in the discontinuous conduction. So these are the some simplified equation. I have just tried, but you can try this equation in whenever now after this uh, uh, lecture, you can just try to derive the equation from the whatever buck converter is there. Timing, you just note down all these equations because these are required for the our some of the one of the example I am taking. So in that we have to use this equation. So this equation you have to write down. VO is equal to VSD, which is nothing but VO is equal to input voltage into the D. Then you can write down the this equation. IR is equal to VO by R. Then the I max equation, I mean value equation, L minimum equation. So just note down the equations. I will wait for the 2 minutes.
Hello, sir.
Yes.
So one doubt. If we are designing a physical buck converter, DC to DC buck converter,
Mm-hmm.
application based, then what are the factors? Means how we will do the component selection, means switching factor and all, means inductor
Yes.
selection and all.
Yeah. So actually, when we consider the miss our practical design, so what you will get, you will be said that I have the input this one, I want to the output this one. Okay,
Yes.
miss I have some source of say 15 volt or something, and from that I want to have the load of say 5 volt. Okay, so I will be
Okay.
requiring this one. Now it is up to the user or the again there will be the some constraints are given for the ripple and that kind of things. So depending on that we have to choose the what is the inductor and everything. If it is not given,
Okay.
then we will try to have the continuous conduction. Okay, and
Okay.
some of the
Okay, sir.
application will define what the ripple content will be there. So I whatever inductor ripple is there, delta IL. So that will be said that whatever your average current is 5 ampere is there. So 5% of the average current, it will be given as a delta IL allowable. Okay,
Okay, sir.
so in that case, you have to keep the ripple 5% of the 5 ampere, means it will be the point not 25 or the 0.25, whatever. Okay, so within that 0.25 delta IL, you have to keep that ripple and choose the all the component. So this is regarding the choosing the L, F and all that kind of thing. Then comes the how you will choose the switches. Again, choosing switch will require the voltage across the switch and the current through the switch. Okay, how much current is flowing through the switch? Either it can be diode or the whatever semiconductor switch you are using. So the voltage trace is coming across the that switch and the current flowing through that switch. So that is the two main factor to choose the any switch. So if you go
Okay,
in the
sir.
market, you will see that you will have the 10 volt switch, then 50 volt switch, 150 volt switch, 600 volt switch, 1000 volt switch, 900 volt switch. Also, 900 switch will have the 10 ampere, 15 ampere, 20 ampere current rating. Okay, so
Okay,
you
sir.
have to calculate the voltage stress across the switch, current through the switch, and then according to that, you see the what components are available, and then you can choose that component. So this is the overall method. Is first we have to define the how you will get the input and output required input and output within the ripple content whatever they are asking. Then from that you will choose the inductor value, then the frequency on that kind of thing. Once you choose, your operation get finalized. From that you will calculate the stress of the switches, voltage stress, current stress of the switches, and you will choose the that devices.
Okay, sir.
Okay. uh, Here, so here one example is given. In the design of buck converter, the peak to peak variation in the inductor current is often used as a design criteria. So delta IL will be used as a design criteria. It can be 5%, 10% of the average current. So which is the delta IL. So delta IL is Vs by Vo by L dt. So from that we can say T, if I take the down, then it will becomes the F frequency. So this is the equation, and you will get the Vo into 1 minus T by Lf. So this Vo is replaced by the uh, uh, T into Vs. So if you simplify, sorry, Vs is replaced here. So this simplification, you will get this equation. From that, I will say L is here. L is nothing but Vs minus Vo delta IL by F. So sorry, L is taken here and delta IL is taken here. So if I simplify, so this equation you are getting. Now if I miss some whatever load is there, so there if I say the 5% of the inductor value, so if I put that value and if I choose some frequency, then I can get the inductor value here. Okay. Same thing which I was explaining to designing the inductor here. You can write down this equation as well. Okay. So one part was we have not considered is the capacitor. Why we require the capacitor? Because see, as in first example, we shown that the whatever output we are getting at the load. Here my load is there, suppose, and by switching on and off, we will get the either the VDC or the VS or the zero voltage across the this one. Okay, but we don't want this kind of the voltage at the output. We want a constant voltage actually. We want a DC voltage here. So it is a like a pulsating DC. This on and off is the pulsating DC, but we want a constant DC. So what we can do, we can use the capacitor here across this. So if we have the capacitor here, and if we apply this type of the uh, voltage across the capacitor, what will happen? Capacitor will start whenever voltage is applied, the capacitor will start the charging here. So for I will just redraw or the okay. So I will just explaining what I was explaining. So uh, this is our load, and we saw that across this load, what is happening? Our voltage, whichever we are getting, this is not the constant voltage. We are getting the this type of the voltage. This is the Vs, and here 0. So this is the pulsating voltage we are getting across the load. But this load requires the constant voltage, constant DC voltage. Either it is a in step down, whatever 2 volts, 3 volt, 5 volt, whatever it is there, but that should be the constant. So what I will do, I will add some capacitor across the load and apply the pulsating to the this capacitor. Okay, so this voltage is getting applied across the capacitor. So if we apply it to the capacitor and if it has a very high value, so voltage voltage across this capacitor, what will happen when we apply this voltage to this voltage? So what will happen? The capacitor will start the charging. So the capacitor charging is like this. Okay, and when 0 is there, so the capacitor has to charging current is there. So capacitor current is flowing through this direction. So the source is applied and capacitor is getting charged. Now when there is no current or uh, uh, there is no voltage, so what will happen? Capacitor will start the discharging. So the voltage across the capacitor will get the discharge. Again you will get the charge and discharge. So you are getting the voltage which is almost constant now. Instead of this pulsating, you are getting the constant. Now if I increase this capacitance to a very large value, if I increase the capacitance, so what we will get? The charging will be the very high, or there will not be any ripple in the charging. Also there will not be any ripple in the discharging, and you will get the almost constant voltage. Okay, so to get the constant voltage or to filter the voltage from the our uh, uh, our buck converter, we will use the capacitor. Again, how we have to choose the capacitor? That will again depends on the how much ripple voltage we can sustain across this load. So to calculate that, again I have used some of the basic formulas. That is the charge of the capacitor, which is equal to C into VO. So change in the charge. So as I said, the capacitor current will charge and discharge, and uh, there will be the charging of the capacitor or the discharging of the capacitor. And over the period of T, you will get the same charging and discharging, because it is a storage element and it will not store any in steady state. It will not store any energy. Whatever energy is charged, the same will be discharged. Whatever it is taking, it will give for the steady state. So I can say delta Q is equal to C into delta VO, which is nothing but change in the voltage of for this period. Okay, delta Q is this one. If I take that one, so the voltage will be change of that one. So delta VO is equal to delta Q into C. Now delta Q we can get from this value. So this is the current going through the capacitor. And if you see for this period, we have the delta Q, which is nothing but the half of the period, because half of the period it is charging and half of the period for the discharging. So this is the discharging period. Again, this is the this is the charging period, and this is also charging period. Half charging here, here discharging half, here discharging half. Now for delta Q, I have considered the half charging and half discharging. So over the time, we can say the T by 2. So for half of the time, you will get the delta Q positive, and for remaining half of the time, you will get the delta Q negative. So same thing I have done. Uh, T by 2, I have considered delta I by 2. So if I simplify this equation, you will get the T into delta IL divided by 8. Then delta VO, change in the voltage, is nothing but the delta Q by C. So the same thing, if I apply here, delta VO into T delta IL into 8C. So simplify this delta IL now. Delta IL, I can have the equation which I have already derived, which is nothing but VO into 1 minus D into T by L. I put it that value here. Again, if I simplify, so T if I take the down, T into T square. If I take the T down, it will become a F square. So I can say delta VO equation will come as a VO into 1 minus T 8 LC F square. So change in the voltage will depends on the frequency square, capacitance value, inductor value, and D value. Okay, and what output voltage you are getting. So all these are getting. Then if I take the ratio, because again here the requirement will be given in terms of the what is the ripple ratio of the voltage. So I can say the 5% of ripple voltage I can accept for the load. If my output voltage requirement is 5 volt and 5% of 5 volt I can accept, then that value is nothing but delta VO by VO. So I will say 1 minus D into 8 F square is the ripple content. Similarly, if I want to calculate from this equation C, I can say 1 minus D into 8L delta VO by VO into F square. So these are the some equations we have derived for the getting the capacitor. So depending on the inductor ripple, we will choose the inductor. Depending on the voltage ripple, we will choose the capacitor. Once we choose the inductor and frequency, we will choose the capacitor. Once this component get finalized, then we will go for the stress of the devices, all devices, that is the switching means controlled switch and the diode. So how much current is flowing through the diode and how much current is flowing through the switch, and what is the voltage across that switch and diode, and we can choose the that voltage and diode devices. This is the overall procedure. So you can write down this C equation also and this equation as well. So I think I will just continue one example and then we will stop. Uh, 5 minutes I will take, not much that. So this is one example of the converter. The buck DC-DC converter of figure, okay, miss the same which we are considering, where input voltage is 50 volt, T is given already 0.4 volt. Then the inductance is given as a 400 microhenry. Capacitance is given as a 100. Then the frequency is the 20 kilohertz and R is the 20 ohm. So this is our buck converter, which already all the values are given. Inductor and capacitor, all value. And load also given. So this is the R is given, then C is given, L is given, T is given for this switch, Vs is given 50 volt, and asked to calculate the output voltage, the voltage across this, the maximum and minimum inductor current, and the output voltage ripple. Okay, so that's why I asked to write down the equation. All these are simple equations, only we have to use VO. VO is nothing but the VO is equal to T into Vs. Okay, so I have the solution as well. So I will just go through directly solution. So VO is equal to Vs into T. Vs is 50 volt. T is given 0.4. So if we multiply, you will get the output voltage as 20 volt. Now maximum and minimum inductor currents are computed. So I max equation I already have, which is nothing but VO divided into 1 by R plus 1 minus D 2 LF, which is equal to, if I put all the values which I got, so you will get the 1.75 ampere. Similarly, I have the equation. If I put all this value, I will get the equation as a 0.25. So if I calculate the delta IL is nothing but I max minus I mean. I max is 1.75 and I mean is 0.25. If we take the subtraction, you will get the delta IL as a 1.5 ampere. So here you can see the minimum value which you are getting the 0.25, which is not 0 or the less than the 0, means that it is in the continuous conduction. So our assumption is correct that we are operating in the continuous conduction under. Now one is asked as a voltage ripple. Again, we have the equation voltage ripple delta VO by VO is equal to 1 minus D 8 L C F square. So 1 minus 0.48400 microhenry is given. Then C is given as 100 microfarad and frequency is given as a 20 kilohertz. So if you calculate this, you will get this value percentage if you multiply. So this is the ripple. So we can say whatever values we have chosen or the whatever frequency we have chosen, depending on that, we'll get the output voltage equals to the 20 volt with a voltage ripple of 0.469%. Okay. Okay. For this, just I have a one homework. So note down this is uh, design. We can say the example which you have to derive and come tomorrow, which we will discuss tomorrow also. Write down, please. Design a buck converter to produce an output voltage of 18 volt. Design a buck converter to produce an output voltage of 18 volt across a 10 ohm load resistance. So what they have asked, we have to design the 18 volt a buck converter which will give the output voltage as a 18 volt and the load resistance is 10 ohm. So across 10 ohm we want a 18 volt. Design a buck converter to produce an output voltage of 18 volt across a 10 ohm load resistor. The output voltage ripple must be not exceed 0.5%. So the output voltage ripple they have asked to keep within the 0.5%. So you have to write the output voltage ripple must not exceed 0.5%. The DC supply is 48 volt. So they have given the input voltage as a 48 volt. The DC supply is 48 volt. Design for continuous conduction current, continuous inductor current. So we have to design the converter for the continuous conduction only. Specify the duty ratio, switching frequency, the values of inductor, capacitor, peak voltage rating of each device, and the RMS current in the inductor and capacitor. Assume ideal component. So whatever I was saying, so here my requirement is clearly given. So that I have the 18 volt requirement output voltage and my load is 10 ohm and I want a output voltage with a 0.5% of ripple. Input voltage is 48 volt. So from 48 volt, I have to get the 18 volt with a 0.5 voltage ripple. And for that, I have to design a continuous conduction. And for that, I have to specify the duty ratio, switching frequency, values of inductor and capacitor, peak voltage rating of each device, and the RMS currents in the inductor and capacitor. Correct? So this you have to solve and come up with the solution. We will discuss this solution for this tomorrow. Clear? Any doubts? So try to go again through the buck converter. Try to analyze all the equation, solve the problem which we have given, design the buck converter to the given requirement. Should we stop here? I don't know Vijay sir is there or not.
Sir, I'm there. I'm there.
Okay, okay.
Any doubts on the topic or the points sir has covered in these 2 hours? sir has given enough explanation, and um, he has deliberately focused on the basic things for the designing of buck converter, and right from the application of power electronics to designing of buck converter, he has given enough information, as well as he has given enough explanation about it, as well as the designing part was excellently done, and he has given some homework for us. I hope you all ready by tomorrow with the assignment of this homework. So, any doubt, you can unmute yourself and you can ask.
Yeah, and just one thing, as I am more focusing on the this converter, because if we understood all these things for these converters, the same thing we are applying for the all the converters. So understanding of the other converters will not take much time or the things if we correctly understand the buck converter. So the similar things we will apply for the other converters, and you will get the results, whatever requirement. So try to go again and read it for the buck converter. Try to solve the equations, derive the equation, solve the homework I have given, and come tomorrow so that we can proceed for the tomorrow's all converters topologies. And of course, today also you can ask the question. And if you get any question tomorrow as well for the buck converter, that also you can ask. If there is no more question, I think we can close. Thank you. Thank you very much for listening me, and thank you for your time.
Thank you, sir.
Thank you. Good night.
Yes, thank you, sir.